So we're going to do four things. We're going to look at the difference between a pulse wave and a periodic wave. Again, a pulse wave and a periodic wave. We're going to look at different waveforms, one which is called transverse and one is called longitudinal. We're going to look at some relationship that exists between wave speed, frequency, and wavelength. And then finally, we're going to be relating energy and amplitude. Energy and amplitude. Periodic. So just to look at our definitions for that. First, a wave itself is just the motion of a disturbance. So think about anything that can be disturbed. So a ripple in water. You drop a rock in a pond that's settled. You'll see the ripples propagate from the center, and they'll propagate radially or outward from like the center of a circle. That's a disturbance. If you saw, anybody ever see the video of the Tacoma Narrows Bridge?
Yeah, that's so cool.
You've seen it? Where like the bridge, yes, the bridge starts to go like this because it reaches resonance frequency, and that's a disturbance, except it's a major disturbance.
Can we watch that video again?
Sure. We'll find a YouTube of it.
Is this bridge that the dude was...
It's a bridge, and I'll show a video at the end. Let's get through this, but it's a bridge that pretty much, it's what's called resonant frequency is reached by the wind and the combination of the masses that are on it, which causes it to start to actually act as if it's like a rope, and the bridge literally starts doing this, and it just completely destroys. It's kind of amazing, actually, to look at. I don't think many people died at all, actually, because there was enough time for people to get off.
So when all of that, it's like someone's
dog a dog was trapped. It's kind of sad, yeah.
Did it die?
I guess, I don't know. Okay, now, the next word, medium. Medium. It's like a substance. It's not like, medium, difficult, easy, okay, levels of degree. But medium is the substance of the material through which a disturbance travels. So, if you're under the water in a pool and you go to yell to the person next to you underwater, usually it's muffled, right? Because the medium is affecting the wave itself. Now,
so would that be higher
say again?
Would that be higher or lower medium?
There's no levels of medium, but there are actual different properties. For example, sound waves depend on the medium it's traveling through. Whereas electromagnetic waves, like light, they don't matter what medium they're traveling through. If it travels through water, it's the same thing. Now, it can be reflected a little bit, and that's different. But the speed does not change for electromagnetic waves. But for examples like sound waves, it does matter. Okay? For example, ever hear you can't hear someone scream in space? That's like a saying. Or no one can hear you yelling in outer space. It's because outer space is a vacuum. And for sound waves to travel, they have to vibrate the molecules in the medium. That's what you're hearing. You're hearing these molecules vibrating until they get to your ear. And then that vibrates your eardrum. They're traveling at such high speeds that you can hear me speak instantly. If the sound of speed was much lower, there would be like a delay from when I talk to when you actually hear me. But because A, we're so close, and B, the speed of sound is so high, you're able to hear it instantly.
So an echo is when the sound wave has nothing, no disturbance, so it just keeps traveling?
Well, yes, but an echo is also like just hearing a wave bouncing off of something. Depends on the type of echo. But if you yell down a hallway and you hear woo, 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 like that sound at the end of the hallway, you can be hearing the sound.
On top of the mountain in the movies, they always do. Yeah.
Sure, maybe at a long distance it affects it, yeah. Mechanical waves are waves that require a medium. So, for example, like I just said, sound. So a mechanical wave is something that requires a medium. So light or radiation or ultraviolet rays, those do not require mediums. Those are electromagnetic waves. Electromagnetic EM waves do not require medium. They are not mechanical. Okay, they are electromagnetic waves. Again, a pulse wave, as we said a minute ago with the quick example, is a single traveling wave, whereas a periodic is a wave whose source is some periodic motion. So the source generates a pulse wave over and over again. And if you keep having pulse waves, you're going to get a periodic wave. Okay, you're going to get a periodic wave. All right, before we get into this, I want to take a look at some animations. And we'll take a look and see what this is actually like. All right, so again, that was our little animation. So we want to talk about two different waves, okay? The two main waves that we have are transverse and longitudinal. We're going to start with transverse. And transverse, the key to remember is that the vibrations are perpendicular to the wave motion. So think about the last example we just looked at with that animation. Which way was the rope vibrating? You looked at the particles. The disturbance along the way, the particles would do this, right?
Yeah.
They were vibrating up and down. But which way was the wave traveling?
Horizontally.
Yeah, horizontally. So the vibration was vertical. The wave was traveling horizontally. Those are perpendicular, right? So that last example, or an example of the rope you're seeing here, with a vibrating end, that was that rotor that was generating the pulses here, this vibrating end. We'll send waves horizontally, but you're going to notice, take a look at this red dot here, and that's what this is demonstrating right here. This point here, initially, is located at the midline. Then it vibrates up, then it vibrates back down to the midline, then it vibrates lower. So the vibration of this wave is actually up and down. And that's why you're seeing this rope going up and down. That's what causes this. But the wave is moving left to right. So what we have here are vibrations that are vertical, wave motion that is horizontal, therefore they're perpendicular, so this is considered a transverse wave. Okay, so transverse is perpendicular motion of the particles with respect to the wave itself. Okay? And when we see longitudinal, you'll see how this is different. You're probably saying, like, well, what the heck could longitudinal be? Okay, but you'll see there is a very big difference. Now, some terminology, and we've already talked about these in our other classes, so these are just kind of review. Amplitude, again, is this gap here between the midline and what's called the trough. See, this is called trough. It's the bottom of the wave. The top of the wave we call the crest. Okay, so the amplitude is this gap here. Or you could think of the amplitude as this gap right here between the midline and the crest because of the symmetry in the wave. We've also already talked about wavelength, and that's that symbol lambda. Okay, I think I spelled it wrong in your class, so correct it if not. Okay, it should be lambda, L-A-M-D-A. I think I put it as L-A-M-B-D-A, just to look in your old notes so we're not confused. But again, the wavelength is simply the length of the wave from crest to crest, or trough to trough. So here, this is the wavelength from crest to crest. Okay, when it starts at a crest and it completes a cycle. Or measured from trough to trough, a wavelength starts here and completes one cycle like that. It's up to you, it does not matter. You could think of the wavelength from here to here. Okay, but this one is a little tricky because you have to remember that you're going to pass the midline and come back through. Okay, so this could be one wavelength, this could be a wavelength, this could be a wavelength, this could be a wavelength technically. Okay, but know that it's one cycle of vibration. Okay, that's what a wavelength is. And the symbol is this little Greek symbol. Okay, you can draw it like that. Looks like a fishbone. Wishbone, not a fishbone, a wishbone.
Upside down.
An upside down
Y.
letter Y, sure. That's a good way to think about it, yeah. Okay, lambda. All right, so that's what a transverse wave is, a transverse wave. Let's take a look at longitudinal. Okay. Longitudinal, the vibrations of the particles are parallel to the wave motion. So if the wave is traveling this way, the particles are also vibrating this way. And the example here is pretty obvious, but let's take a look. A spring. If this spring is compressed, or like say it's pulled and it's let go, the vibrations are this way of a spring, right?
Yeah.
A spring oscillates back and forth, and that's the way the wave also moves. It moves back and forth. So you're going to see that this wave is like pushing it this way. It's like a sound wave. Sound waves are longitudinal because when I speak, the molecules vibrate outside my mouth. They vibrate with the air molecules until they reach Garrett's eardrum. And then they vibrate his eardrum so he can hear what I'm saying. So those waves are vibrating this way, which is parallel to the actual motion of the wave itself. Okay? So you see these you see these horizontal vibrations of the wave, but it's also moving horizontally. So these are parallel. Okay, so longitudinal waves vibrate parallel to the wave motion itself. The graph is very, very misleading and it's tough to look at, but if you look at this graph along with this, it makes a little sense. Take a look at the spring at x1. See how it's compressed here? And then at x2, the spring is stretched. X3 is compressed. X4 is stretched. So what they're actually looking at here is the compression as a positive value and expansion as a negative value. So at x1 there's maximum compression. So x1 is this crest right here because the density of the spring is very high. But here it's stretched. So there's a low density of spring. There's not a lot of spring there. So we're considering that this trough. It's down here. Then it's compressed. That's back up here. Then it's stretched. That's back down here. Well, what are these regions? These regions are when there's no compression or no stretching. That's right here, where there's like a normal spring. And here, in between the compression and the expansion of the spring. Okay, this graph, again, is a little bit more misleading. The other one is one you want to really look at.
How do you know it's parallel again?
Because the molecules are vibrating this way on a spring, right?
Yeah.
They're vibrating back and forth, and the wave is getting sent down the spring. So the direction of the vibration is horizontal. The wave is moving horizontal. Those are parallel. Parallel vibrations are longitudinal. As opposed to the previous example where the wave on the rope was vibrating up and down, yet the wave was traveling left and right. Those were perpendicular. Okay, so the key words here are parallel for longitudinal, perpendicular for transverse. All right? Okay, let's take a look at one of our formulas we're going to use here. And this is really the only formula that we're going to ever use for this section in 12.3. And what we're going to look at is the speed of a wave. And I'm going to quickly show you the derivation of this one because it's easy. Okay, so start with your general formula. Remember, velocity equals displacement over time. And if you think back to your graph, the displacement of one wave was called the wavelength, lambda. So we think back to this graph here. Okay, this was called lambda, right here. It's like my displacement of the wave. So we're replacing this x up here with lambda, both of which are displacement. This is the wave displacement. The time it takes in velocity terms can be replaced with tau. What was tau? The period, which was measured in seconds, right? Yeah. The period is time. So we're replacing time with tau. Okay, so again, lambda is still meters, tau is still seconds. So this is still meters per second. Clear so far?
Yeah.
Now, think about tau from last class as 1 over omega. Remember, the period was 1 over the frequency. So we replace tau with 1 over omega. So this tau becomes 1 over omega. But when you divide by a fraction, you multiply by the reciprocal. So think of this as lambda times the reciprocal of 1 over omega, which is omega over 1. Okay, remember, division by a fraction is multiplication by the reciprocal of the denominator. So lambda times omega just becomes omega lambda right here. So your final formula that you're going to need to use is right here. Okay, again, you don't need to memorize the derivation, but just so you know where it came from, but that's the formula we're going to use. The speed of a wave equals the frequency omega times the wavelength lambda. Again, the speed of the wave, v, okay, equals the frequency omega times the wavelength lambda. Okay? Again, omega times lambda. And now I'm saying speed even though it's v, I know for velocity. Okay, but for these cases, we're going to look at just positive values of velocity. So we're going to say the speed here. Okay, speed. Any questions on this?
No.
This is going to be mainly plug and chug with these equations or these questions. Take a look at an example. Plug and chug. Plug in and chug through the problem. So, let's look at an example. The wavelength of the sound wave produced by a middle C on a trumpet is approximately 0.72 meters. That's the wavelength. If the speed of sound in air, is 343 meters per second, then find the frequency or the pitch of the note. Okay, find the frequency or the pitch. In band or in music, you say that the pitch is a middle C. Okay, but in physics, we're going to talk about the frequency in hertz to understand what the actual vibration is that we're looking at here. And each different note, on a scale has different frequencies. So even though like a C might sound like a low C and a middle C and a high C, they all sound the same as far as like if they go together or if they don't go together. They have different frequencies though. And that's why you see along a piano all the keys. So you go through all your notes from A through G, okay? From A through G, and then what happens is you start over again, another set of A through G with sharps and flats along the way. So you're going to see that these different octaves, they're called octaves, are separated. So we have a wavelength of 0.72. So let's write down our givens. We've got a speed of sound in air of 343 meters per second. And what are we looking for? We're looking for the frequency, omega. Okay, so again, plug and chug. These kind of problems are not going to be difficult here. We know the formula. What's the formula from the last part we wrote down there? Jack?
V equals omega times lambda.
Good. V equals omega lambda. We're solving for omega. So Garrett, step me through. What do?
Plug in.
Okay, I can plug in, or if I want to solve analytically, divide by?
Divide by the upside down y.
Good, lambda. Okay? Canceling lambda out, you'll get omega is just V over lambda. So you can plug in, or you can solve analytically like this and just solve. Okay? Take your 343 and divide it by 0.72. What do you end up getting for this? Approximately to the nearest integer.
476.39.
Good. And to the nearest integer?
0.38 repeating. So 0.4.
No,
Sorry, integer, whole number, Paul. Nearest whole number, 476, okay? My units of hertz, let's make sure we know where those are coming from. The meters cancel, don't they? What am I left with when the M cancels? Isn't there a 1 up here, really? So I'm left with 1 over seconds. 1 over seconds, remember, that definition was hertz. 476 hertz are the frequency of a middle C on a trumpet. Clarice? Z, yes, Hz. Okay, hertz. Hertz. I think so. 1013. We've got one more example to do. Okay? Next example. Calculate the wavelength of an X-ray, which affects, like for example, when you get X-rays on your body and they want to see like if you have a broken bone, the wavelength is extremely important. Only certain wavelengths will give a good picture. So they have to be able to have the correct wavelength. So let's take a look at an example here of calculating the wavelength of an X-ray, which is an electromagnetic wave. If its frequency is 3 times 10 to the 12 megahertz, this is where our prefixes are going to come in a lot. Remember all those prefixes in the beginning of the year, they weren't as used? With electricity and magnetism, lots of prefixes, so make sure you're used to them. If that is the frequency and the speed of all EM waves in empty space is 3 times 10 to the 8 meters per second. That is the speed of light in a vacuum. 3 times 10 to the 8 meters per second is the speed of light in a vacuum. Which is why the speed of light is so enormous. Think about that. 3 times 10 to the 8 meters every second. 3 times 10 to the 8. 3 times 10 to the 6 is going to be 3 million. This is 300 million meters every second. Imagine that. 1 second goes by and somehow you've traveled 300 million meters. It's incredible how fast light is. Okay, when you think about it. That's why it takes light 8 minutes to get here from the sun. The light that we see right now is 8 minutes old. So people always joke, the day that the sun stops giving off energy, which is far from now, you won't know until 8 minutes after it happens. It's kind of incredible to think about. The sun's going to stop giving off light, but 8 minutes later, suddenly you're going to see darkness, and you're like, oh, the universe stopped 8 minutes ago. And you're going to have darkness. Well,
What's the capital M in front of
mega times 10 to the positive 6. So we're going to have to talk about what to do here, okay? So let's write it down. Okay, I'm going to draw my units. Actually, I'll leave them for now, sorry, because I left them in the last one. So I have megahertz, and then I have meters per second. The meters per second I'm good with. I can leave that alone. But I've got mega, and I want it to be hertz. And mega meant 10 to the 6. So we have 10 to the 6 and 10 to the 12, which gives me 10 to the...
multiply them? 10 to the...
Well, you multiply.
72.
You multiply, but when you multiply, you add exponents.
Oh, 18.
There you go. So omega is really this. That's what it really is.
Oh.
But it's really...
If you were raising it again, then you would multiply, right?
Okay? That's what omega is going to become. Remember, the term or the prefix mega right here, this capital M, means times 10 to the positive 6. That's one of the ones you should have known. Okay, so we put that here. 12 and 6 gives you 18. Okay? Now, on your calculator, some of you have been having some trouble. If you want to write 3 times 10 to the 8 on the calculator, write 3E8. And where's that capital E? You press second and then look for the EE. Paul, let me look over your shoulder real quick. It's second and then the comma, which is above the number 7. So press 3, then press second, comma, again the keystroke above the number 7. It'll bring up a capital E, which means times 10 to the, and then put the 8 there to show the 8th power.
Why are we multiplying this these two?
Because it was megahertz,
Yeah, but why?
and we have to have it in hertz.
Why is the other one 3 to the 10?
The units of here were just meters per second, right? For velocity. So this is your velocity right here.
What do you mean to
It'd be
Okay.
3 times 10 to the 12th power.
Correct, but then it's times 10 to the 6th power. Because to get rid of the mega, you need to put times 10 to the 6. Because a mega means 10 to the 6. So again, to get rid of this mega right up top, okay, this M, we need to, in its place, get rid of the prefix, it's gone, but put 10 to the 6, because that's what it means. Like kilo, we would put 10 to the 3rd. And that becomes 10 to the 18th. Okay? Now, what we're going to do is write this as 3E18. So these are really the quantities that we're looking at here. Okay? With our units simplified, these are the two quantities, V and omega. And we want to figure out the wavelength. So again, let's write our formula. V equals omega lambda. And we're trying to find lambda, so divide by omega here. Cancel. So take your velocity, 3e8, and then divide that by 3e18. Omega. Okay? Yeah, what are you going to notice? The 3's are going to cancel, leaving behind a 1. And what's the times 10 of the what? Yeah, negative 10. Okay, so this is what you should get. Again, you're doing 3e to the 8 over 3e to the 18. These cancel, leaving behind a 1. And this is really, remember, this is really 10 to the 8th, and this is 10 to the 18th. 10 to the 8th and 10 to the 18th yield 10 to the negative 10. Okay? On your calculator, you'll probably see 1e negative 10. And the units here for lambda are going to be meters. The reason we know this is because this is meters per second, and this is hertz, which is 1 over seconds. Seconds cancel, leaving behind meters in the numerator. So this is what you're going to end up getting for your wavelength. Now, this is not really in scientific notation. Anybody remember what we can do for this? What is times 10 to the negative 9? How can that help me? 10 to the negative 9.
Well, wouldn't you just put it 1 over 10 to the 10?
Okay, so we can write it as 1 over 10 to the positive 10 meters. Yes, we can definitely do that, Paul. Good. But if I wanted like a prefix that might reduce this or make it more seemingly possible, like what's 1 times 10 to the negative 10 meters? Does that mean too much to you? You have any idea what that length actually is?
It's like, it's really small.
It's really small. Okay, that's what I would think. It's really small. So maybe we should put units of like nanometers or micrometers or centimeters or millimeters or something like that. Okay? No, but I wanted just so you can see for now. You don't have to. But you have an idea of what this actually turns into. Garrett?
So for the problem set, there are like some equations like halfway through that involve like pi. Do you want me to like?
Yes, use pi on the calculator and give me the decimal. Correct. You left it in terms of pi?
Yeah.
Just multiply that answer and just write the new number next to it.
Right.
Yeah. A lot of the time you're going to see leave answers in terms of pi and like in math and when you're looking at different formulas. But for period, you want an actual numerical value.
Okay.
So you're going to use that. So you could write this, by the way, as this. This is what a nanometer is. A nanometer is times 10 to the negative 9. So another way to write this is to get rid of 9 of these negatives and just tack on the nano. Because remember, a nano is times 10 to the negative 9. So this becomes, if you multiply it back out, negative 9 and negative 1 is what gives you back to the negative 10 up here. Again, this is 10 to the negative 9, 10 to the negative 1. So you could write this simply as 0.1 nanometers, which is extremely, extremely small for our wavelength. Okay? So when we talk about nanotechnology, X-rays have been working on the nano level and wavelengths for a long time. But now we're able to fabricate things on the nano level, which is where nanotechnology is coming into play. So for example, like bulletproof vests now in the military and armed forces, the fibers that are used, that are intertwined, are on the nano level, which is what gives them such high strength. Okay? So nanotechnology, sure, it's new in that sense, but it's been around for a long time. Okay? X-rays are a simple example of nano. Let's look at one last thing about it. We're not going to an example, so you don't have to write this down. But if you're reading this in the notes, you can read it later. So, can I get somebody to read that paragraph at the top for me, please? Nice and loud. Garrett, go ahead.
Waves transfer energy by transferring the motion of matter rather than the matter itself. The rate at which a wave transfers energy depends on the amplitude of the wave. The greater the amplitude, the more energy a wave carries in a given time period. For mechanical waves, the energy transfer is proportional to the square of the wave's amplitude.
So that's just proportionality constant. So if you want to know how much the energy is going to be transferred, think about the amplitude and square it. You should know the relationship, so maybe write that down. E is proportional to a squared. So if the amplitude doubles, you square that, so the energy would quadruple. If the amplitude tripled, that would be going up by a factor of 9. If the amplitude went up by 5, then the energy would go up by a factor of 25, and so forth and so on. Okay? So, if we think about this, the amplitude of a mass spring system over time is going to decrease. Right? You let a spring go, and the mass does this, and eventually it stops, right? The amplitude stops or gets smaller, because you're losing energy to friction. So if you lose energy, you lose amplitude. That's why those oscillations settle out. That's why the pendulum eventually will stop. Okay? So this is your example here. This wave has a higher amplitude. This would have more energy. Okay, so E1 would be greater than E2. Is that logical? Think about the ripples in water. The ripples in water, the bigger the ripples, don't you think about that has more energy? If you see these little teeny ripples, that's not going to really affect you. But you see these giant ripples in like a wave pool, that's when you think about energy of the waves actually pushing you. Okay, so remember, amplitude and energy are directly related, but the amplitude is the square. Okay, the square. As one goes up, the other goes up. Or the other goes up.